going to do 6.3. Volume by slicing. Okay, so let's draw a picture. Say this is our function f of x. So this is just some random function which that's continuous, right? I drew it without lifting up my pencil. Let's say we want to rotate this around the x-axis. So I'm going to do this little swirl. I'm rotating it around the x-axis. So that's going to look something like this. Wow. My artistic skills are out of this world. So I'm rotating. I get a 3D shape, right? Let's say I want to calculate the volume of this. Let's say this is the top of my container. So this is, let's say it's like, it looks kind of like a flower pot. And this is the bottom of my container. Okay, the artistic skills there weren't as good, I apologize. But I get something that looks kind of like a flower pot, right? How do I calculate the volume of this? That's what's tricky. So let's look at a slice of this. So my slice, oh, that's not good. So my slice is actually a cylinder, right? So any slice is a cylinder. Oh goodness. Is a cylinder. Obviously, it depends on the slice that I take out because obviously the radius is different, right? Depending on my slice. What's the volume for a cylinder? Pi r squared h. Okay? So the volume of a cylinder is pi r squared h. Let's put that into the context of this picture. Here's my r. If this is the x-axis, what is r in terms of my function? Well, pi is always pi.
X.
What's the radius?
It's the
Y value.
It's the y value, good, right? The height of this is your y value, which is f of x, right? Okay, so this is my radius, which is actually my y value no matter where I take it. So that's f of x squared. What's my height? The height of my cylinder. What do we call it with Riemann sums? We called it delta x, right? The length of my box was delta x. So delta x. Okay, so that's the volume for one of my cylinders, right? But I have a bunch of cylinders. So I would say that the volume equals the sum from A to B of pi times f of x squared delta x. But remember when we talked about the definition of the integral? I remember. We took the summation to equal the limit of the integral, right? That was the definition of the integral. So here, thinking back to Riemann sums, how do we get the best approximation? The smaller the delta x, right? Okay. So let's do that. So the volume equals the limit as delta x goes to 0 of the summation from A to B of pi times f of x squared delta x. But when we did the definition of integral that we all remember, the limit of the sum that went to the integral and delta x goes to dx. Okay, so let's write that. Okay, so we've just come up with our formula, right? This is going to be the formula. So we have the volume of any rotational solid equals pi times the integral from A to B, because all of this goes to the integral. All of this goes to the integral. I could have pi inside the integral, or I can take pi outside, times f of x squared dx. And that comes from pi r squared h, right? Does that make sense? So we just derived the volume of how to slice a solid, right? Any solid that the curve of the solid can be written as a function, we can calculate the volume for. Okay, let's do an example. Okay, so sometimes this is called the disk method. So we're just taking disks. We're slicing our shape into disks, and that's why it's called the disk method. Okay, let's do an example. So sketch and find the volume. Created by the curves y equals e to the x, y equals 0, and x equals 0. About, and x equals 1, about the x-axis. So again, look, I have the disk method, I have f of x, my bounds are x, and I have dx. So this is all in terms of x. To rotate, let me write that. So this is all in terms of x to rotate around the x-axis. Okay? So solution. Let's draw a picture. here's e to the x. Okay, y equals 0 is where? The x-axis. Where's x equals 0? The y-axis. And where is x equals 1? Here, right? It's a vertical line. Okay, so what I want to shade, what I'm trying to rotate is this. And I'm trying to rotate it around the x-axis. I always like to draw this little circle, and you'll see why in a little bit. If you don't want to draw it, you don't have to, but it helps stay organized, I think. I'm rotating it around the x-axis. Okay, so let's come up with the formula. Volume equals pi times f of x, here's my function, is e to the x, squared dx, right? That's my function. What are my bounds? I need x values, right?
0 to 1.
Yep, because that's my x value for where I'm rotating it, right? Okay, so from 0 to 1. Put that into my calculator, because we know how to integrate this, right? It would be a simple U substitution, then fundamental theorem of calculus. And I get 10.03590.585. Your homework will probably say give the exact value, so in this case you wouldn't put pi in there, right? Volume is what? What's my units? Units cubed, whatever it is. Whether, I don't know what they'll talk about. Okay? Good. So that's if I have a solid, right? But let's say I wanted to make a vase or something like that. Bless you. What? So this is A, the disk method. We're going to talk about B, the washer method. So just like before, how we did the area between curves, this is going to be pretty similar. Okay, so let me draw a picture. So really, this is just memorizing a formula, right? Pi r squared h, but you guys know that. Okay, let me draw something else. So here I have my same f of x. Let's say I have some g of x. And I want to rotate this solid around, right? So So I'm rotating this around to be something like this. Let me do it in a different color. This is your G, and this is your F, right? So I'm rotating this around.
Okay, you're rotating it around the x-axis.
Yep, rotating it around the x-axis. And I have some sort of a 3D kind of thing again, right? Okay, so now we're going to do the same kind of thing where let's look at a slice. Okay, let's look at a slice here. We'll take a slice. What does it look like? Well, it looks kind of like a cylinder, right? But it has an empty hole inside. because I'm taking that middle part out. Right? Okay, so let's figure out the volume of this. Who's got an idea? It's very warm.
Find the area of the whole, the volume of the whole thing.
The volume of my cylinder.
And then the volume of the inside is the back.
One more time.
And the volume of the inside, so like the basically
So,
another cylinder and subtract.
yeah, so you take the volume of the outside cylinder and you subtract the volume of the inside cylinder, right? That makes sense. Just like we did the area between curves, we took the area of the big one minus the area of the small one. So we're going to do the volume of the big one minus the volume of the small one, right? Okay, so let's see if we can come up with a formula for that. So the volume of the big one is what? Pi r squared h. I'll call this capital R. Okay? And I'm going to subtract the volume of the small one, which is pi r squared h. The h is going to be the same, right? Because we're talking about the delta x or the h of the cylinder. So that h is the same. The thing that's different is that this is the little radius. So I did a capital radius and then a lowercase radius. Can you see that in the picture? Is that a little hard to see? Okay. So let's put it in terms of this problem. What's my radius again?
For the big R, it's f of x.
So I have pi f of x squared h minus pi times what? G of x squared h. Okay? Does that make sense? Okay, so we could do all that limit stuff, right? How we did before, we could write it as the limit, the summation of the cylinders, then we could take the limit as delta x goes to 0. But from all that, we're going to get the washer method. And that formula is the volume equals pi, right? I'm factoring out pi from both. Delta x from both, or h equals delta x in both, which in terms of the integral equals dx. And then I have the outside radius minus the inside radius, right? So I have f of x squared minus g of x squared. And it's each of those squared individually from A to B. So let's write this even simpler. So this is all in terms of x, right? My bounds are x, my function is in terms of x, and I have dx. All x values, rotating it around the x-axis. Okay, so I have f of x, I have g of x in my formula. Okay, that's great. Can somebody remind me what f of x is and what g of x is? Well, f of x is my big radius or my outside radius, right? Big or outside. And g of x is my little or inside. That's its radius. So you're kind of thinking it's like a top minus bottom, right? But it has to be your outside radius and your inside radius. So I really like to label that in my picture. Figure out, depending on your axis of rotation, what's your big radius, what's your little radius.
Yes, I mean, you could be rotating it around.
Because we're going to, yeah, we're going to.
Y equals 2 or something.
we're going to change this to be where we're rotating it around
Right.
too. So you have to know your big radius and your little radius. No matter where you're rotating, draw this. Every time I like to do big R, little r. Okay, so let's do an example. So this is example 2. Sketch and find the volume. By rotating the area. Okay, so find the volume by rotating this area around the x-axis. So first step is we need to draw this thing, right? Okay, so I have 2 parabolas, right? 2x minus x squared is a downward facing parabola. And here I have y equals x squared. That's an upward facing parabola, right? So let's draw. Y equals x squared. Obviously that's symmetric, right? And here I have something like this. Y equals y equals 2x minus x squared. Okay, so this is the area I want to rotate, right? And I'm going to rotate that around the x-axis. Okay? So let's figure out what the big radius is. That's r, right? That's my big radius. So my big radius is the purple. And my little radius is right here, right? I always like to draw what that is. Okay? So now let's do the formula. Big radius squared minus little radius squared, right? So volume equals pi times the integral of big radius. My big radius is the purple, which is 2x minus x squared. And that's squared. Minus the little radius, which is the pink, which is x squared dx. Okay, now how do I determine my bounds? When they equal each other, right? And they're the x values, right?
You just, unless it says show how to get the
No,
bounds.
you have to show how you get the bounds. Okay, so we have to figure out the x values for these points, right? So to find bounds, we set the functions equal to each other. X squared equals 2x minus x squared. So I'm going to solve this, right? So I get 2x squared minus 2x equals 0. I just added everything to the left-hand side. Now I'm going to factor out a 2 and an x, right? 2x, and I get x minus 1 equals 0. So I get x equals 0, and I get x equals 1. So those are my bounds. So then this is something that we can integrate, right? I'd have to FOIL this, distribute my exponents, right? Make sure you're FOILing this. Don't write this as 2x squared minus x squared. FOIL it, and then do this, right? But at this point in the class, we don't need to calculate the integral every single time. Unless we're explicitly told to do so, right? So here I got 3 pi over 4. So now that we know we did all the techniques for calculating the integral, this is something we should be able to integrate, right? Oh, no. Sorry, that's pi over 3. Pi over 3. Okay? So this is when we rotate it around the x-axis. We're just looking at the big radius squared minus the little radius squared, right? What if we're rotating it around the y-axis? So let's write down the washer method in terms of the y-axis. So did everybody get all this? I'm just going to go up here. Let's see if we can put this in terms of y. Volume equals pi times the integral from a to b of f of y squared minus g of y squared dy. So this is all y values, including the bounds, rotating it around the y-axis. Okay? So there's not much that's different, right? It's still big radius, little radius. Okay? So let's do an example like that. So sketch and find the volume. Created by rotating the area bound by the curves y equals x to the 2 over 3, y equals 0, and x equals 1 about the y-axis. Okay, solution. Obviously, the first step is to draw the picture, right? Y equals 2, y equals x to the 2/3. This is x equals 1, and this is y equals 0. So I'm trying to rotate this, right? This is the area that's enclosed by the curves. I'm going to try to rotate that around the y-axis. So now I'm just looking at my picture and trying to identify the big radius and the little radius, right? So here's my little radius, and here's my big radius. let's see if we can write that. I have volume equals pi times the integral of the big radius, which is 1, and I have x equals for that, right? That's good. Minus the little radius, which is y equals x to the 2/3, right? dy. So good. So Caleb already recognized that if I write this as x to the 2/3, that's not everything in terms of y, right? So I need to say y equals x to the 2/3. I need to solve for x equals in order to use that. So how do I do that? Well, I use the rules of exponent. If I raise this to the 3/2, then I multiply those exponents, right? For rules of exponents, I multiply those exponents, and I get 1. So I'm raising everything to the 3/2. So this is y to the 3/2 equals x. And then that's what I have, y to the 3/2. And what are my bounds? I have from y equals 0. What's my y value here? 1 from this, right? From x equals 1. That's a y value. Oh, no, that's not right.
So
But it's 1.
With something else, you could set the x equals equal to each other, right?
Yeah, it is something else, right? It's not, that's where you get this. So to find bounds, we set y to the 3/2 equal to 1 from these two, right? So that's how we get y equals 1, not from the x equals 1. Sorry, that was incorrect. Yes. So then you could use rules of exponents and say this is 1 minus y cubed dy, which is easy to integrate using the power rule. But from this, you get 3 pi over 4. But this would be a good example for one to do on the test, saying show all of your work, right? The directions for the whole test say show all of your work, so that means show the integration unless otherwise stated. Okay? Okay, so we'll do more next class. Did I already assign the due date for